All right, so Joe, I'm going to read from my lovely little screen here so that you can see the color. Joe is a computer engineer, hardware hacker, teacher, dad, honorary doctor, proprietor of Grand Idea Studio, and partner in offspec.io. And the name of his presentation is That Time I Hacked a Hardware Wallet and Recovered $2 million. So everybody will want to be friends with Joe by the end of the presentation if you're sharing your $2 million. Joe, do you need me to keep them entertained for longer?
I don't know. Can you guys hear me?
Yes.
Yes. Okay.
You're
so
good?
No, I think I'm
Fabulous.
good. Right.
Take it away.
That was easy. Thank you. Wow. So this presentation is going to be a lot different than everything that you've heard today. I am mostly a hardware hacker. I grew up also at the age of 7 doing things that I shouldn't have done, figured out how to make free phone calls when I was 10 years old, got arrested when I was under 18, so did not go to jail, luckily, and ultimately found my path sharing, my passion and my skill of hacking and of hardware hacking with people that they can then go and use to design better systems or to attack systems as well. So really my goal nowadays is to work on fun projects that are interesting and then share that information with other people, and then you can go off and hopefully do something useful with it. So yeah, this presentation, this is not just clickbait. This is actually... Let's see, is this going to work? No, I'm going to go manual here. So this is a true story. This is a project I worked on last summer, and we just came public with it. I don't know, what was that? When Munir contacted me a couple weeks ago. So this is going to kind of be a supplemental talk with a little more backstory to our video that came out, and there's going to be a link to that, and I'll show some screenshots of really going through the whole process of what it takes to hack a piece of hardware that just happened to be a hardware wallet. And this is something that was at a time where COVID restrictions, still being in the US, are still in place. I wasn't traveling like I normally do. I was kind of sitting around the house working on some of my own projects, but the timing just worked out where I got this email completely out of the blue. And I get a lot of emails out of the blue, and they normally aren't as well constructed as this. Usually it's, can you hack this thing for me? Can you do this? Can you do that? But this one was actually, sounded pretty good, right? It's like I'm reaching out because of an issue with my Trezor wallet. And I'll get into the specifics of the Trezor. In 2017, I bought some cryptocurrency and haven't touched the wallet since. When I was moving earlier this year, which would have been the end of 2021, I think that I accidentally threw out the recovery seed. So this kind of sparked this interest, and I was like, oh, that seems kind of interesting. I haven't really hacked on hardware wallets before. My wife was like, yeah, just do it. You're not doing anything else. Like, you might as well do something interesting. So that was February 2021, and in the summertime, so it took 3 months of kind of research, which we'll go into, that ultimately led to breaking this wallet. And it did end up being a really interesting project, but also shows that when you are hacking on something, no matter how many times you've used the process or the tool or how many skills you have, nothing ever goes to plan. So it really shows the real life, kind of real world process of things. So this is, I'm not going to go all the way into cryptocurrency and how it works and all of that stuff, but this is the Trezor wallet that stores essentially your private key that you need for cryptocurrency. If you don't deal with cryptocurrency, that's fine. If you're doing any sort of encryption at rest or anything else, you're going to have keys, right? So you can almost apply this more generally as a hacker trying to get access to your keys that can then decrypt all your data at rest or in transit or anything else. So standard kind of encryption process. So yeah, this is a general purpose microcontroller inside of this Trezor device. Your protection basically is a pin that you will choose, and that protects your private key. So my goal was to get the private key out of this device that's supposed to be, protected, and it is somewhat protected. And then with that private key, I then have access to the funds that this person lost, and then we could go and use that private key to create a new wallet, and he can have access to his funds, and he can transfer some of it to me, and then he can take the rest. So it was just a really interesting challenge, and I thought it would be fun to do. One of the security mechanisms here, actually, from a user perspective, is, like most phones and everything, you enter your PIN. If you enter it too many times incorrectly, it's going to wipe the data. So he had tried a couple guesses, and I think he had 2 or 3 guesses left before it was going to wipe his, $2 million. At one point, it was actually $3 million of value off of this thing. So he kind of gave up. So just brute forcing the PIN wasn't an option. We had to go to lower level to see if we could, access and defeat the security inside the microcontroller that's running this Trezor device. In this presentation, I am kind of, I'm picking on Trezor because they're the ones that I actually broke, and others have as well, which we'll see some of that. But as with everything, any product is vulnerable, right? Security just all comes down to how much effort and how much value is it for an attacker to actually go through and break the system. In this case, the guy had, a couple $1 million. That seemed worth it, especially because the system that I ended up using, maybe a couple $1,000s worth of equipment, and you could really do it with $5 or $10 if you're really going, budget on it. If it was something where somebody contacted me and had maybe $100, I might still be able to do it, but is it worth my time? Probably not, because like I said, no process is ever repeatable and ever works the same every time, especially as you'll see with the attack that I used. So you have this balance, kind of security, but any product is breakable. It just depends on what that value is. So Trezor now, other wallets, later. Oh yeah, okay, so as I started doing this work, I do make a lot of videos, and usually they're pretty bad. I take my phone and I hold it up, and I'm like, here I am, basically for other engineers, right? It's not something where I want to spend a lot of time doing production and making it look good and good lighting like actual YouTubers. So most of my videos are just me explaining some technical concept, and a lot of it ends up being around more on the engineering side of things than the unengineering or the hacking side of things. So when I started working on this, my wife comes in and she's like, you should really be filming this. Like, people need to see what your hacking process is, not your engineering process. Because I teach a lot about hacking, which is what I mostly do, travel around and teach, but not a lot of it is kind of public. So as I got more into getting closer to the actual attack and realizing, okay, this is actually going to be a feasible thing, I called up a friend of mine who's a professional cameraman and said, okay, when we're going to do this on this guy's real wallet, after I can prove it on some reference devices, like, let's film this, and let's not make it a crappy video on a phone. Like, let's do it for real and try to make like a really good video about it. So we did. And again, I'll show you some screenshots of that, but it was really a fun process to not only share the experience, but tell that story with all the dramatic aspects. So hopefully, after this presentation, you'll want to go watch the full video on YouTube. And even though you're going to know the outcome, it's still, pretty interesting. So before I get into that, I'm just going to do a couple slides, kind of general purpose hardware hacking, just to get us in that mindset, since we haven't gone into that today. So this is a process that I use when I'm hacking hardware, no matter what it is, no matter how long I've been doing it. This is always the process. And people go, well, hackers, think outside the box and they don't follow rules and processes. And it's like, well, actually, I do. Within these, you can kind of deviate from that, but I like having this structure anytime I look at a product. So if you're on a product design side of things, you can look at this and be like, all right, now I know how hackers are going to kind of compartmentalize. Maybe I should think about these things. And I could talk for days about, every single section here, but I won't. But this is kind of it. So, getting access to a product, getting as much information as I can about the product through online resources, through reverse engineering, through, depending on what it is, maybe I have to social engineer somebody at a facility or at a company to send me information. It really depends. But getting what I can. For the Trezor device, it happened to be open source, which is great. So all the information I needed was already available. That doesn't mean open source is bad, because if a product was closed source, it would just take slightly more effort to reverse engineer the system first to get the information that I need to proceed. So it was nice in that case. Product teardown. So once I have my physical access to a device, figuring out how to open it, get access to the circuitry, and then looking at the circuitry, maybe creating some sort of block diagram or some sort of schematic or some structure of how the main components connect. Because then I can look at that and say, okay, I want to target this thing which has the data that I'm going after. Buses and interfaces is the next level down. If I see there's 2 chips communicating, maybe I want to monitor communication. In the case of my attack, there was 1 chip, the microcontroller, and I wanted to get access to the debug interface, which is an interface built onto the chip itself that lets normal engineers access the chip, access memory, step through code, just like you would if you're like debugging a piece of software. And of course, in this case, there was security around that I had to defeat. But that's sort of the buses and interfaces level. Memory and firmware. So say once you get access to an interface, what do you want to do with that access? Do you want to extract memory? Yes, in my case. Maybe somebody's getting access to a system and they want to modify the memory. So the system's still going to function, but it's going to do something a little bit different, right? So if we think more about maybe like a hardware implant or malware, think about that on a computer, but now apply that to a smaller type of device, an embedded system, so a portable, electronic device. And then sometimes you have to go chip level. So really the silicon die itself, instead of looking at the integrated circuits on the board, you're looking within the chips. And what you do at a chip level, silicon level, you decap the chip, you remove the cover of the chip, and you're looking at the silicon, is really a microscopic circuit board. So you can use all these same steps that you would at a higher level hardware hacking process now at a chip level, except you need multi-million-dollar pieces of equipment to do that. Some hardware is going to require that, for sure. This device, not so much. So our main thing that we have to deal with for this Trezor device is based around microcontroller security. So microcontrollers being general purpose CPUs with peripherals around them. They're used in every possible electronic device you can think of nowadays. There's nothing I can think of really besides maybe like a toaster oven. No, probably even toasters use microcontrollers now. You could still see some things with discrete logic, but you normally don't because it's easier to just use a microcontroller that's a general purpose computer running whatever code you write than trying to do something custom, right? It's using a bunch of packages instead of just system out, hello world. And that's kind of what happens. So people just grab a microcontroller that has all the features there. Every microcontroller is going to have some mechanism to protect the code that's running on the microcontroller and possibly other features as well. And that's really going to depend on the vendor. Different vendors have different security mechanisms. They have different access control mechanisms for different memory regions. Sometimes there's multiple security methods that you have to defeat. It just completely, there's no standard. It's just up to the vendor. How you potentially defeat the security is going to change, depending on if it's checking a register value, if there's a physical fuse that's being set, if there's a password you need to enter to enable certain features. It's all completely different. So there's really no kind of silver bullet to breaking different things. The cool thing is that there's some classes of attack that are, make a lot of these things vulnerable no matter what security mechanism is there. Regardless of what security mechanism there is, the chip normally configures itself on power up. So if you think about a computer powering up, right, you have your power on self-test or your UEFI and all the low-level stuff before it loads the bootloader maybe, before it then loads the kernel or the operating system and user code, whatever it is. Chips kind of do the same thing. So when you have a microcontroller, you have some product that you're turning on, the chip itself configures itself before it starts running user code, which is really kind of cool when you think about it. Within every microcontroller, you're going to have something called boot ROM, and that's essentially hard-coded functionality or hard-coded code within the chip, and that's going to power up the chip, get things configured in order to then, say, set the crystal oscillator functionality or to set security or check security or whatever it is, get things ready before it runs user code. And that's what we're going to end up targeting, is the configuration state when the chip, any chip, but in particular we know for the chip that we're targeting, during the configuration stage, it's setting that state of security. And there's even times where if you know that, you could cause something to happen before it actually checks the state of that security to bypass it through like a race condition or something. But we're effectively going to use something called fault injection to force our way in at the exact time when it's doing that check. So the Trezor uses an STM32, ST Microelectronics F205 series, general purpose microcontroller. There are some microcontrollers that are actually designed to be more secure. So secure elements that have much harder hardened security areas or specific areas to store, say, an encryption key. Those usually require a confidentiality agreement to be signed. Companies are not as forthcoming with information, so it makes it hard from an engineering perspective to actually design with those. We see those for certain things. A lot of banking stuff, financial systems use those. But in the case of Trezor, they intentionally chose a general purpose processor, which does have some security, but not the level of what they should be using, because it didn't require a confidentiality agreement, and anybody could go and grab the data sheet of that part and see how it functions. So there was sort of a business reason to going with a less secure part, hoping maybe that it wasn't going to be compromised. The problem, though, is now with the attack that I use and other attacks that that have not been as publicized, any STM32 F2 series microcontroller is vulnerable no matter what. So that's a business decision that maybe is problematic, and maybe they're okay with that. As far as the microcontroller security of that STM32, there's basically 3 states. So you have this RDP level 0, which basically means everything's open, completely unlocked. Usually you do that for development, and then when your code is ready and you're in production, you would lock the chip and send it out. You have RDP level 1, which is kind of this intermediate state where you have debug access. So as an engineer, you can still connect to the chip. You can access RAM, so volatile system memory, but you cannot access flash. So it's a very limited functionality, and really the only reasons you might want to do that is if you want to have something running in RAM as a test program or things, but it's very limited. And then you have level 2, which essentially locks everything out, no debug access. Not only is there no debug access, if you try to connect to those pins that are the debug interface, it's like they're not even there. So it's really supposed to be gone completely. Between levels, not that this really matters, but between level 0 and 1, the unlocked and the middle state, you can go back and forth. If you go from level 1 to level 0 by downgrading, you erase all the memory. So that's not going to work in our case. Like, we wouldn't be able to do something that we could, get back to level 0 to give us full access, because that's going to erase the whole chip. What you can't do, once you're in level 2 and you lock that chip to RDP level 2 when you're in your manufacturing process, you can't go back at all, says the manufacturer. Meaning you can't ever make changes to that thing. You can't do very easily, you can't do firmware updates unless you have built in some additional bootloader functionality and blah, blah, blah. But the debug interface is not there. What we end up taking advantage of when we do our actual attack is the chip inside the Trezor is at level 2, so completely locked. We're able to downgrade it to level 1, which gives us access to RAM, and then it just happens, and I'll show you this, that the information that we're trying to get, the secret key, the private key, is stored in RAM while the system is running for some reason. Because it's there, we can essentially knock down the security, get access to that RAM through the debug interface, and get the contents out. It's really difficult, or probably impossible, or I guess I should say unlikely, to go from RDP level 2 all the way back to 0, because there's just too many bits that need to flip. Essentially, when we're going from 2 to 1, there's like a register that's being read on that power-up that says, what is the register value? If it is CC in hex, then it's going to say, okay, I'm locked. If it's AA, then it's going to be unlocked. If it's anything else, and I think it's actually a 32-bit register that it's reading from. So if it's anything else at all, it goes to level 1, which means it's very easy to induce some sort of failure to go to level 1, but to basically force a read to go from a specific value, CC, to a specific value, AA, is like way less likely. So very easy to go from 2 to 1, and that's what we're going to take advantage of. To do that, we're using a technique in the hardware hacking world called fault injection. And this is essentially, I kind of call it an advanced technique, even though we're starting to see it used more and more, of intentionally getting a system to fail in a way that we could take advantage of. So if we know that the chip is powering up, and at a certain point in the power-up cycle, it's checking the state of security, and we want something to fail at that exact point in time, we can try to inject a fault into it through a number of different ways. and that's going to usually just crash the chip. Sometimes we get lucky and it does something else. It changes the software path. It returns a 0 for whatever the function was running, or something like that. And it's very unpredictable. Like, you can kind of start narrowing it down if you do a bunch of characterization of a chip and figure out what configuration values are going to cause it to crash or not, and all of these things. But really, we just need to do that once, right? We just need to be lucky one time to inject a fault where the chip doesn't crash, but it actually gives us access. So it's really like a really, really fun technique. And once you have learned about fault injection, you kind of want to do it to everything. It's like if you have a script and I wonder if the script is going to work against this system or this system or this system. Same thing. It's like once you know how to use fault injection, you want to use it on everything. And the scary thing is every microcontroller system is vulnerable to fault injection at some point, unless it's specifically been designed to have countermeasures against that. And even sometimes the countermeasures, so we're going to use something called voltage glitching or voltage fault injection, which we're essentially power cycling the chip really fast, or like causing a brownout, like flipping the light switch on really fast to have it do something. There might be a countermeasure for a voltage fault injection, but that might not work against an electromagnetic fault injection where we're just injecting like a quick electromagnetic pulse without physical access to the chip to cause something to happen. So there's all these different methods. We're using voltage. There's clock glitching as well, where if you can control the heartbeat of the system through the crystal oscillator or whatever oscillator circuit is driving the heartbeat for the digital system, you can inject your own heartbeat and basically give the system like a heart palpitation. And have it get an extra heartbeat in there, and that's going to throw stuff off. Electromagnetic, temperature, optical. If you decap the chip, you can actually shine a laser onto the chip itself and induce faults if you do that at the right time. So there's a whole world of academic study into fault injection, but also into the hacker side, the more practical applications of that stuff. So just so many ways to go. But fault injection is one that I'm very familiar with because of this, and it's just so easy to implement. The way fault injection really works is every chip has defined operating parameters, meaning the vendor can design a chip and say, we're going to guarantee functionality within this voltage range, within that frequency range, within that gray box. Anything outside of that gray area, we can't predict what's going to happen. So it's you as the engineer are responsible for making sure the system operates within those parameters, which is fine. But hackers don't have to worry about that. So our whole thing is, all right, we know what the normal operating conditions are. What if we operate outside of those operating conditions for a very quick point in time? What's going to happen? And it's very hard to protect against every possibility of what an attacker is going to do, right? Whether it's on software, hardware, network. We can kind of predict based on known attacks that have happened and our kind of exposure on the network and if we're using cloud or whatever it is, but we can never predict everything. So we're taking advantage of operating outside of that area to basically pull a power line low very quickly to cause a problem. Fault injection is really easy to talk about, and I'd actually been using similar slides in some of my classes for years, talking about fault injection and what you can do, but applying those is really where things get tricky because every chip is different, even every different chips in the same family. So if I bought 10 STM32F2 microcontrollers, the location of where I actually have to do my glitch at the right time to defeat the security is going to vary slightly because of manufacturing tolerances and temperature and all these other things. So even if you have the general structure, it's always going to be a challenge to figure it out. But really, you have to know when during the boot process are you going to glitch? How wide does your pulse have to be? How long are you turning off the lights for, essentially, in order to cause a failure? There's a lot of back-end work that has to happen before you can actually do the thing and then hope the thing works. So that's a little bit of it. When I got the email about hacking the Trezor, I did some Google searches and realized, the Trezor's been hacked before through a number of different ways. Some of those methods had been patched. Trezor actually does a really good job. If you go to their website, their security page actually says, yes, here are vulnerabilities that have happened. We have fixed these. Here's how we fixed them. Like, they do a good job of acknowledging vulnerabilities and fixing them. Though I still don't think they enjoyed my video very much, because even though they had fixed the problem, it kind of made it much more of a known issue. So sorry about that. That's just the way it goes when you're designing products, right? Someone's going to find a problem. So there was already information about breaking certain versions of the Trezor out there. So when I got the email from Dan, from the client, I was like, okay, this is going to be, I could just replicate that work, right? Shouldn't be too hard. Not the case. So the two main presentations that were out, there's a lot of them, and I have resources at the end of the slides if you want to really dig into the process. And the slides are already up on my website, and they'll be available through Munir and Isaka as well. But wallet.fail and chip.fail. So two presentations by friends of mine, it turns out. And I hadn't really paid attention when these came out. This was 2018 at 35C3 Chaos Computer Congress, or Communications Congress. And then they followed up with one called Chip.fail at Black Hat US 2019. And I'd watched the presentations, but because it wasn't directly applicable to me at the time, I was like, that's cool. Fault injection, like they compromised a bunch of wallets and a bunch of chips. Like, this is awesome. But it didn't really hit me until I got the email. And I'm like, okay, now I got to go study these presentations and figure out what they were doing. So I thought, again, I could replicate this work. They had already figured out, by the time I was doing my work, kind of the general timing and process to prove that the STM32F2 could be glitched, fault injected, to downgrade security from RDP level 2 to level 1. Through some reverse engineering, which they get into all the details, they basically figured out there's some power on reset that happens with the chip. Then the chip reads the boot ROM, and during the boot ROM process, some point in there, it's reading from that RDP register and doing its compare before it runs the user code. And they had actually reverse engineered the chip to the point of looking at power consumption. So the amount of power that the system is using as the chip is powering up. And it's very minute. It's not, watts and stuff. It's tiny, probably microamps of current that they're measuring, but you can see different changes in the structure. So as the chip powers up, there's some amount of power consumption, and then when it starts reading from internal ROM or internal flash areas, there's a little bit, and then it starts executing user code. They could kind of time this because they could load their own custom code into a test chip. So they know, okay, as soon as that IO pin goes high, or as soon as that LED goes high, I know it's running my code. So they can kind of time where their known thing happens with what the chip is doing and try to narrow down the area where they need to actually attack. So this was already known, which was great. It turns out it was helpful, but it wasn't really helpful because I was crafting my own set of code to try to replicate this work because they hadn't released the code to do so. And there's still, even within this range of when it starts reading from the boot ROM area to where it's checking is like pretty wide. So it takes a lot of guessing and trial and error. On one of the slides about fault injection, I mentioned that usually you have to modify your target in some way before it becomes more easily vulnerable to fault injection. And there's a number of different ways to do that depending on the chip. For the STM32 series or the F2 series, they have what's called an internal voltage regulator. So you have power coming into the chip. That's going to power everything. 3.3 volts is, there's a range of voltages you can feed into a chip. But this, say, 3.3 volts coming in, that's going to power some of the peripherals, maybe your memory. But generally, the CPU core voltage is going to be lower. And if you look at a PC, you have core voltages of 0.9 volts or 1.2 volts, very, very low. So this chip has an internal regulator that will take in the user-provided voltage, step that down to what the CPU core needs. When we're doing our fault injection, we want to directly affect the CPU. We don't care about any of the other peripherals or anything like that, at least for this attack. We want to hit the CPU because that's the thing that's processing our code as it's running. It just so happens with this family of chip, when you have an internal regulator, on the output of that regulator that feeds the CPU core, it's going to need some external capacitance to help clean up the signal, kind of smooth the power a little bit. And it's more effective to do that with an external capacitor. instead of trying to build that onto the chip itself. So the engineer or the developer of a system using this chip needs to have external capacitors on there. If we want to get access directly to that CPU core voltage, which we do because we want to do the voltage glitch on that, we can just remove the capacitor and now we have access. And then there's another trick you can do too, because the regulator is still going to be trying to provide voltage to the core. If you drive a voltage in on that line slightly higher than what the regulator is providing, it shuts off the regulator. So now not only do we have the voltage going, can we control the voltage going to it, we can also do our glitch and effectively bypass the regulator. So when you're hacking on systems, you probably, and I'll show you this in the actual Trezor, you have to take some capacitors off the board because we don't want to smooth out our power lines. We want them as susceptible to small glitches as we can. But generally that doesn't take a lot of time. It's just you have to reverse engineer enough of the system before you do that so you know which things to remove from the board. So like I said, I thought I'd be able to just replicate this work, build up my test platform and get my hardware. I had done a lot of trial and error. I would say that there's a relatively steep learning curve to getting fault injection working, and that's just because there are so many bits and pieces of the thing that have to go right. Everything has to go right at the exact same time for things to work. And the challenge is, especially in the case of a system where the debug interface is shut off completely, you don't even know if what you're doing is even on its way to being successful or not. So you're kind of just shooting in the dark until you hit something. You're like, oh, that's a surprise. And that's what ended up happening. So at first I did some electromagnetic fault injection. And I had a bunch of tools from Colin O'Flynn, is a friend of mine who runs a company called New AE Technology in Canada. And he basically makes a lot of the fault injection tools designed for engineers to kind of test their own things. But he has created these tools to make these attacks much easier for normal types of people. So he had sent me a bunch of stuff. So I started with EM because I figured if I'm doing this on somebody's actual device, I don't want to, I want to reduce the amount of physical modification I have to do on it because I don't want to take the risk of something breaking. So I started doing some electromagnetic injection instead, which didn't require physical access. And you can actually see some of the results of as I'm shooting EM, electromagnetic interference at the chip at certain points in time, trying to get it to leak information. The screen would display all sorts of weird stuff on it. So that was cool. But it turns out that I was erasing memory a lot because you're just blasting it with electromagnetic interference and you don't know what's going to happen. And that's cool, but it's not effective for an actual attack, right? I couldn't take somebody's device with millions of dollars on it and do this and just hope it's going to work. So I kind of went down this path of trying EM, but not appropriate for this. Then I started doing more attempts of voltage glitching, and you can kind of see some of my attempts of using some of the tools and wiring stuff up. And I tried a couple times of taking the actual chip directly off the Trezor device itself and putting that into a socket. So I tried some other configurations. But nothing I was doing was causing the chip to glitch. And I could not figure out what it was. Was it my voltage regulator set up to try to bypass that voltage regulator? Was it my debug interface connections? Did I not solder those properly? Was my code doing something weird? Was my JTAG hardware working? I mean, there were just so many things. And that's what took 3 months, is trying to figure out exactly what, make sure the setup was correct. Even after watching existing work. It even got to the point where I could not glitch at all. I was like, am I doing something wrong, or did ST fix the problem? Did they remediate this problem, and the chips that I've been using for testing, maybe they've already fixed the problem and it can't be glitched anymore. So I reached out to them and sent them an email through their website ticketing system, and was not expecting a response. And I basically said, hey, I'm developing with your chips, the STM32. I'm aware of some vulnerabilities, as far as fault injection. Have you fixed those? And within a day, they responded, to my surprise, and said, we're aware of some of the work. There was no revision done to the F2 in regards to fault injection. So for me, that was a real positive moment, because now I knew that the chips were still vulnerable. So every version of the chip was still vulnerable, which means that it must have been something of my fault, right? But at least I got rid of that potential that they had fixed the problem, and they didn't. So that was very satisfying. And that was really like the catalyst I needed to keep going, because it was a dark time for a while. And I'm like, why am I even a hardware hacker if I can't replicate my friend's work? And I didn't reach out to them either, because I just felt weird asking, which you shouldn't, right? Because it's, hacking is all about knowledge sharing and information. But I just felt weird asking them. Of course, I talked to them after the fact and kind of figured out some of the stuff I was missing. But this was enough for me to go back and say, okay, let's look at every single thing, individually. And what I ended up doing is creating my own code that had basically 2 loops in it. So I was trying to glitch my own user code, not working on the security or anything like that. I just needed to prove that I could inject a fault and affect the system. So I did that first, kind of starting at the basics, like the most simple kind of thing. And eventually, through a lot of trial and error, you can kind of see my little screenshot where I'm showing how many times I'm trying to, or how many times I'm looking at the loop, and how many times is the loop having values that indicate that it's been successfully glitched. And we can see it's like I tried 802 times, and 135 of those had successfully glitched. So finally I did it. And this is a screenshot where I text my wife at 11:51 p.m. And then the next morning she woke up and said, yay, like I did it. So now I could prove that I could at least affect program flow of the chip. Now I can try to apply that to the RDP security level, right? So it's taking these little steps. Even though you know something's possible at the end, you still have to take these little steps to get there. So this is a screenshot of some code I'd written, some Python code, to basically loop through, starting at a certain point in time, which really is when the reset line of the chip goes high. There's a certain delay before you do your glitch. And that's what the chip.fail and wallet.fail research had shown. There's some weight between when the chip powered up to when it's checking, but even there, you still have a range. So I had a loop that would basically go through this range and try a glitch over and over and over and over and over again. If that didn't work, I would do it again, and I would increase my glitch a little bit, my width, over and over and over and over. So just over and over again, trying to see if the debug interface would magically appear. All of these errors is, one of my attempts each time, basically saying we can't connect to the chip because the debug interface doesn't exist. We don't even see it because that's RDP level 2. And then magically one showed up. It said, hey, I found it. Device ID. So that's actually the chip responding to my query through that debug interface that shouldn't even be there because it's RDP level 2. And it says, this is my device ID, which corresponds with that chip. So I knew that attempt actually was able to show me the right thing. So now I knew, finally, I can downgrade from RDP level 2 to RDP level 1, which means now I can try this on an actual Trezor. What I also needed to do, so I bought a bunch of Trezors to use as my reference devices as well, because the customer, he didn't want to fly all the way to Portland and have me do this, if I couldn't prove it. So I loaded up my reference devices with the exact same version of firmware that he had, and we could verify that by running an official tool from Trezor to see what it was. And it just happens, like I said at the beginning, this version of code was copying the critical information that was in protected flash memory into RAM on PowerUp. And it just so happens that after this version that we had, that goes away. So the code is not loaded into RAM automatically anymore. There are other vulnerabilities for later versions of firmware. And also, like I mentioned, it doesn't even matter what firmware version it is because the chip itself is vulnerable to fault injections and other types of attacks. So it doesn't matter what user code is running because we can get all of it, at a lower level. But in this case, version 1.6.0 is copying this stuff into RAM. So now I can kind of put together this whole system of, I can power up the chip, I can try to do fault injection. If I do the fault injection and re-enable RDP1, which gives me access to RAM, hopefully the contents that I need have been copied into RAM, and now I can just use the debug interface that I've opened up and extract all the stuff. So it really is this multi-step process. here's my ultimate setup using a couple different tools here. First one is the chip whisperer. So this is one of the tools from New AE Technology that has a bunch of kind of Python-based interface to it. So if you're not really a hardware hacker, but you want to hack on hardware, and you're more like writing code, you can write code to basically configure this tool to glitch at a certain point and to do what you need to do. So there are lots of other options. Also, it just so happened that I was using this one. There's a chip whisperer Lite. There's a chip whisperer Nano, so like an educational version. There are open source versions. Thomas Roth has one called the Debug and Dump that's based on a Raspberry Pi Pico. You can really do it with a just maybe an FPGA or even a microcontroller, say an Arduino with an analog switch or a mux. So you can really go the range for fault injection. It doesn't have to be high-end tools. I just like using tools that I know are going to work, because then when I run into problems, which I did, I can at least rule that out as the possible offender. So the chip whisperer does the fault injection. I had another tool called the Phi Whisperer, because the security and the boot ROM of this chip is only read on power up. So every time I need to re-glitch, I need to fully power cycle the chip. When I'm doing that in situ, inside of a product, the only real way to do that is to power cycle the entire product. And to do that, since it's powered through USB, is to either physically unplug and replug each time, which I'm not going to do 10,000 times in a row. So this Phi Whisperer is actually a USB protocol analyzer that can not only analyze the data that's coming across USB bus, which could be really handy for other types of hardware hacking, and it could even provide a trigger for if it sees certain data at a certain time, it could provide that to the chip whisperer and then glitch on something. But all I was using it for is just turning on and off the device. So I could just plug it in, send a command over Python, power off, power on. So I would do that over and over again. And then I had my debug interface, standard hardware debugger. This is a Sager J-Link, one of my favorite types of tools. Just a standard JTAG interface, which is an industry standard debug interface. And that all comes together through this kind of interface board that I made just to make the wiring a little bit easier. But it's a relatively simple kind of setup. This is what the board looks like inside. Again, this is open source hardware as well, so I could look at the schematics. I can look at the circuit board layout. Even if I didn't have that, I would figure it out relatively easily, right? So closed source doesn't mean you're better. Down along the bottom, those 6 pins, that's the debug interface. So I could wire that up to my Sager J-Link, and of course, it's not going to work until I do the glitch. We have the buttons, there's some capacitors. So some of the capacitors are there that I have to remove and then wire up some circuitry to actually connect to the core voltage to do my glitch. So you'll see what that looks like a little bit later. But here's a schematic of the system, so an electrical roadmap of how everything's connected. And it's a relatively simple system. But you can see the modifications I made are very few. I added a pull-up resistor on the reset line, and I removed the capacitor from the reset line, because we're using the reset. When the chip powers up, the reset line goes from low to high, basically telling us, okay, the chip is active and ready. With the capacitor there, it's going to make that slower, and we want like a really crisp rise time to measure our starting point. You could probably do it without removing that. And then here are the 2 capacitors that are those external capacitors for the internal voltage regulator. So I removed those and then attached my connector, my SMA connector, which connects up to the chip whisperer, directly to one of those core voltage lines. So now I can provide the voltage that I need through that connector and then glitch it when I want, based on when the reset line goes high. So not really a lot of modification, right? It's a couple capacitors, and that resistor I had added onto my little adapter board. And that's it, just wiring some stuff up. But you still have risks, because if you solder the wires wrong of your debug interface to your hardware, you might successfully glitch, but you might never know because you're not communicating properly. So not having any response from the chip makes things, really, really tricky. Anyway, so I did all of this work over a couple months, proved to myself that I could reliably do fault injection. prove to the customer that I could reliably do fault injection on actual devices and extract recovery seeds. And I made little videos to prove that, and got comfortable enough that we decided that he should fly out. Even at that point, like, I was still nervous about it. My wife was like, "Oh, it's fine. You've done it, 4 or 5 times. Like, it's not going to be a problem." But me knowing, like, yeah, just because I've done it doesn't mean it's going to work this time around. And if anybody's given a live demo, right, like, oh, okay, the demo works when I'm, not on stage. When I'm on stage, it doesn't work. So you just don't know. With the camera guy there and everything, it was pretty stressful. But anyway, yeah, so these are screenshots from the video. So he actually flies to Portland, and we meet for the first time. I'd also, by the way, when I was kind of vetting him to make sure he wasn't completely insane, we had a phone call, Zoom call. He seemed well-spoken and everything. And now that I actually have done this more for other people, we actually have like a full KYC process, background check and everything, because I'm just not going to have start doing business with random people, right? Especially in the cryptocurrency space. You just don't know who anybody is. So yeah, so he comes over. We do our handoff of the device. So he carried it, hand carried it with him, and he entrusted it to me. And then what I had said in the video, I'm like, you're not allowed to touch it at all. Because that was the thing of, like, I wanted to have it and not have somebody intrude and mess something up at that point. So the first step, kind of just like in that process, the hardware hacking process, I had to do a product teardown. I had to open up the device to get access to the circuitry. This product says, we have ultrasonic welding to create a one-piece housing to make it tamper evident that somebody, that you'll be able to tell if somebody opens the device, which is great for a particular type of threat, which would be maybe, say, somebody, you leave your token in your hotel room, somebody opens it and it's visible that they've opened it, and then do an attack with it. For what we were doing with a legitimate device in my lab, that security feature did not matter. And actually, it turns out the ultrasonic welding was very weak, and there's a seam along the 2 pieces of plastic. So I just took my knife and very carefully pried that open. By doing it with my reference devices first, I could tell where the critical circuitry was. So I knew, which way to hold my knife, which side, up or down, should I cut to reduce the risk of something bad happening. But yeah, so it didn't take much to open it up. This unit has something called conformal coating, which is a coating that you usually see on industrial equipment, SCADA equipment, stuff that is outside, automotive. So it's some sort of coating that protects the components from moisture and corrosion and dust and all of those things. And it had it on this device, which I think was a pretty good idea, right? Because you're carrying this thing around in your wallet. If something, or in your pocket, something gets into it. So I needed to remove that coating so I could properly solder my connections to the JTAG interface, but then also heat up the components enough to remove them from the board. So I used a pen, standard conformal coating remover pen, kind of generic term for it. And there's different types of coatings, but I basically just bought a bunch of different pens, which are different types of solvents, and figured out which one worked the best to give me that clean access that I needed, and just rubbed that all over the board. I didn't even really need to do it anywhere else other than the connector and the capacitors, but I just wanted to have a clean environment in case I needed to do some probing or testing or other things. Then I prepped the board. So here you can kind of see I have some wires coming off with my connector, and all my reference boards are up at the top. So that's all the other times that I had done this. And I'm soldering on the connector, and I'm had removed the capacitors. So preparing the board, like I just talked about, getting it all ready. Then we hooked it up and started the fault injection process. And here is, these parts should now all look familiar. But we have the Phi Whisperer, the J-Link, the Chip Whisperer doing the glitching. And you might notice, like, oh, there's an SMA connector here on my little interface board, and then there's one over here. During my testing, I wasn't sure if the quality of my glitch, like if the strength of the glitch, or if the waveform of the glitch was good enough to cause the fault injection. So I added a different SMA connector much closer to the board to try to get as pure as I could of a square wave, or of a pulse. It turns out that's not actually necessary, but once I verified my attack, I didn't want to start messing around with parameters at that point. I was like, all right, I know it works. I'm going to try to do it this way. So here's what a fault injection glitch looks like, which is not really that exciting unless you're actually doing this. And when you see it, you're like, okay, at least I know it's glitching properly. And you can see, I'm actually going to play a little video of this. It was very slow. So we're going through, I think it was like 10,000 attempts of different widths and different spacings or timings. And we can see it's like, okay, there's 1, there's 2, there's 3, and it starts again, 4. It's very slow, right? It's like 1 every couple seconds. This was just based on my implementation. A couple weeks ago, I was trying to modify this for a different project and realized that I could do it, I think it's like 5 or 6 times faster, which makes it much easier for me now to locate where the glitch needs to happen in a much faster time. This took us about 3 hours to wait for that certain time. And I basically just simplified the query to the chip. So if the chip does open up, the debug interface on RDP level 1, I can do a much simpler query that's much faster to tell me if it's there or not. But this is what it was at the time, very, very slow. So we set it up, and there's some drama that happens in the video as well around setting it up, and things didn't look quite right compared to my original implementation, so you'll have to watch that and see what happens. And then we wait. So we ordered pizza and hung out for a long time. And then magically, at some point, we see a bunch of errors. We don't see the success because it's like down at the bottom of that log. But just while we're sitting there, the glitch worked. And we're like, yes. So now we can actually see a response from the chip saying, like what we saw before, like here's the device ID. Now we've successfully connected to the chip. We've kicked down the door of RDP level 2, re-enabled security, gotten to RDP level 1, which means now we can access RAM. And at this point, we're hoping that the contents that we want are in RAM. And it actually turns out too that this, at the time with this implementation, my glitch was still causing the chip to crash, but it was crashing after it had loaded the contents into RAM. So very timing specific kind of thing. And I've refined that as well since then. But it was really, we just got lucky. So once we knew this was gonna happen, we said, okay, at this point, now we can run our code. Actually here it connects and then it runs code to dump all the contents of RAM. So now I had a file on my computer that I called sram.bin. That was the RAM area. And then if we did it right, and if the timing worked out just right, inside of that memory dump should be our recovery seed and our pin and a bunch of other stuff because all of it was stored in clear text. Yeah. Yeah, that is definitely a valid comment. They did end up changing that in future firmware versions as well, but that just means you have to extract more of the metadata contents that are encrypted. Actually, you have to get all of them. And then since you know what the encryption method is, you can just brute force what the pin is that's used to encrypt that. So, again, it's just another attack. But in this case, it was all in the clear. So all I had to do is run strings to actually see the results. And we can see the recovery seed. That's a bunch of individual words corresponding to our private key. We had the pin. And the guy was like, no, I thought it was a 4-digit pin, but it was a 5-digit pin. So it really shows like, human memory. You might think you thought something, but it's totally wrong. But yeah, what we needed was there, right? So then we could set that up on a new wallet and get our money back. And we were all very happy. There's the camera guy. And there's Dan, customer, and of course me. And that's the hardware. And Dan actually took that hardware home and put it in a frame and put it up. And he was very happy after that to get his funds back. He tells the story in the video, but he basically had researched a bunch of different places to invest and put in, I think it was $25,000, and his friend put in $25,000, which is a huge amount to invest in anything, I think, yet alone like an unknown cryptocurrency, because it wasn't Bitcoin. It was one called Theta, and took a huge gamble that paid off. But no way could I ever do that. So it eventually worked out, which is very cool. And he actually thought the process was so interesting and realized he's an entrepreneur and an engineer, so it was fun to go through the process with him. He's like, well, I can't be the only one who has this problem. So he actually invested in this little company that we started on the side to break wallets. which is turning out to be a lot of fun and a lot of work. So we only try to pick the ones that are interesting, because I don't want to turn it into like a mill where I'm just sitting there doing the same thing over and over again, because that's boring, and that's not what hacking should be about. So it's picking the interesting projects, technically challenging projects, projects that really are going to help somebody, and being able to use my skills in a way that are not just standing on a stage, but like could really change somebody's life, which is kind of cool. So ultimately what comes out of this, what I learned from it, are a number of things. One of them is that, any general purpose microcontroller that you're using, any security features that they have on there maybe are good for certain types of things, depending on what information you're trying to protect, or again, how much effort is it for the attacker to get to it. But security that's enabled on these devices, might not be suitable for what you're actually doing with the product, or what you're trying to save within that device. So there might be a situation where, again, like Trezor took that intentional step to use a general purpose microcontroller, knowing that their encryption or that their private keys and other information is only protected by that standard general purpose security of ST. And they took that as a known thing. Whereas maybe now if you're designing a new system and you know this attack, you might say, okay, maybe I'm going to try to find something that's maybe designed a little more purpose-built for security or for secure storage of things within the microcontroller or whatever it is. But yeah, that's just something to be aware of, is if you're trying to protect something in a general purpose microcontroller, don't base your whole thing on that. Fault injection, as much as we hear about it nowadays, and there's amazing papers and amazing research, all of it takes time, and it's very dependent on so many things. And even just trying to replicate that work that had existed, trying to do it on something, or know that I had to do it on a device that was not mine, and I didn't just need to hack it to come up and talk about it, I had to hack it in a way that was going to work and be successful. That really changes things, and there's so many external factors, right? So I talked about, like, the temperature of the room is going to change some of the configuration or some of the variance of timings. Sometimes the way the manufacturing of the silicon, there's going to be variances in the components on the chip level that's going to affect things also. Not by a huge amount, but just different enough where I can't just run the same code with the same timing every time. I have to have a loop, and there's going to be some range. And that's why being able to do it fast makes that a little easier. But it's also why no matter how many times you do it, you never know what's going to happen, which is part of the thrill, but also kind of scary. And then, the quality of the glitch, what type of glitching circuit you're using, whether it's a crowbar where you're pulling things, straight to ground like the Chip Whisperer, or if you're using an analog switch to do it maybe a little bit softer. There's all these different parameters. And that's why usually what happens is if you try to characterize the chip the best you can first using your known code and all of that, and then try to apply things afterwards. But it's a huge, long process to do that. Yeah, so no matter how many times you think you have it right, you're just never sure. When it does work, though, it literally feels like magic every time. I've probably done this now probably over 100 times with test devices and things and other people's devices, and it's just every single time when it hits and you see it, you're like, this is the coolest thing ever. And it's just, that's what hacking really is, right? It's like when you can bend a system to your will, whether it's through hardware or software or whatever, like that's the beauty of it. And it's just, from an engineering perspective, like I'm sure the designers are not very happy with that, but it really feels cool, especially when it's a system that's completely not listening to you at all, and then you kind of kick it, and then it like suddenly does something for you. It's awesome. So here are some of the resources. These are clickable links. So again, if you go to my website, grandideastudio.com, if you just search for Trezor, it's going to come up. It's on my main page right now, but the slides are already up there, so you can click on those. There's a lot of other existing research that had come out before the wallet.fail and chip.fail stuff. There's some work that came out afterwards. And then our videos down at the bottom. And then The Verge wrote an article. Kim Zetter wrote a great piece for The Verge about our process and everything. So yeah, lots of different things to check out if you're interested in fault injection or getting involved in hardware hacking at all. This is really only one attack of so many different ways of breaking hardware. And sometimes it's much easier than this. So that is the end. And that's the back of Dan's device. He wanted me to sign it, which is cool. But yeah, so thank you for listening to this story. And do we have time for questions? Yes, we have time for questions.
Yeah, indeed.